All right, in section 10.1, we talk about relating relative maxima and minima and curve sketching. So, if you're talking about a relative maximum or relative minimum, it's different than a global maximum or global minimum. Global max or min means it's the highest point everywhere. Global minimum means it's the lowest point everywhere. So, on Earth, the global maximum is Mount Everest. But if you look locally, you can say Mount Rainier is a relative maximum point. And if you could find some low point, maybe along the beach somewhere, you could say that's a relative minimum somewhere. It's not the lowest point on the Earth. That would be at the Mariana Trench, 3 miles below the sea level. But if you're talking about just within a small neighborhood of a certain x value, you can pick a point that is a maximum, or you can pick a point that is a minimum. And these are called relative max and relative mins. All right. Now, before you get to a relative max or min, the function itself is increasing, and then at that point it changes to decreasing, or it's decreasing and it changes to increasing. So if you're moving from left to right and you go increasing, decreasing, you know the point that you just passed is a relative max. If you go from decreasing to increasing, you know it's a relative min. So if you look at the derivative, which is what this is the derivative of the graph we just saw, you see that the derivative is positive y values for -1 or less, and it's negative y values between -1 and +3, and it's positive y values for greater than 3. And so if you look here, greater than 3, it's increasing. Less than -1, it's increasing. Between -1 and 3, it's decreasing. And so notice the derivative will be below the x-axis when you know that your original function is decreasing. Where the derivative is above the x-axis, that's where the function is increasing. And where the derivative equals 0 is where you have a possible max or min point. So you can have a relative max, relative min. It can be a nice smooth curve, or it can be even a sharp point. Either way. Typically these x values that will give you these relative max or mins, or possible relative max or mins, are called critical values. These are places where the first derivative is either 0 or undefined. And these might give you a critical point. It just depends on what you find when you plug x into the original function. Now when you take the first derivative, set it equal to 0, you find these critical values, in this case x1, x2, x3. If you check a value to the left and right of each of these numbers, you can find out what the sign is for that derivative in that entire region. Since these are the only places where your first derivative is 0 or undefined, then that means everywhere else it has to be positive or negative. Now in each region it's going to be all one sign, because if it was positive in this region and negative in this region, it would have to cross over at some point to give you a 0, and we know there are no zeros here because we found all of them already. And we also know it's not undefined because we found all the places where it's undefined. So all you have to do is check one number, one x value to the left of this, one x value in between these two, and between these two, and you want to check it with the first derivative, and you don't care what your answer is, you just care what the sign of your answer is. And whatever the sign is, that will dictate what the function is doing. If you get a positive, that means the original function is increasing. Get a negative, it's decreasing, increasing, and decreasing, and so on. And so you see that there's two ways that a function can have a relative max or min at a critical point. It shows here you got a relative max, and here you also have a relative max, and here you have relative min, and here you have relative min. So how do you find where it's increasing, decreasing, where the function has a max or a min, all these relative max and min points? Well, there's a 5-step process here. You first find the first derivative, step 1. Step 2, set the derivative equal to 0 and solve that. And you'll either find places where the first derivative equals 0, or you'll find out where the first derivative is undefined. Typically you're dividing by 0. You take those critical values and you plug them into the original function. This is important. Original function, f, not f prime. And that will give you the y coordinate for the function. So here we found -1, and we plug -1 into the original function, we get 11/3. So now we know one of our critical points is -1 11/3. Then we found 3 is another place where the first derivative equals 0, and we plug that into the original function, and we get -7. So now we know another critical point is 3, -7. Now the next thing is you take those critical values and you divide up the number line, like this, and you divide it up based on your critical values, -1 and 3. And all you have to do is check a value in each region. So you might want to check -2, and when you do, you get a positive number, so it's plus. And you might want to check a number like 0. 0 is between -1 and 3. And f prime of 0 is negative, so these are all negative. And then you might want to try a number greater than 3, like 4 or 5. They try 4 here, and they get a positive number. So you know it goes plus, minus, plus. So it's increasing, decreasing, increasing. So now we can say this is a relative max, and this is a relative min. And this is what our graph looks like. And again, it does have a relative max and relative min. Example 1 asks you to do all 5 steps. So you take the original function and you take its derivative, set it equal to 0, factor it if you can, typically you can, and you'll get different values. And here are your 3 critical values. Now you want to find the y coordinate for those critical values, so you plug into the original function. Use f of x here, and you get your y coordinate. Now you've got 3 critical points. Now, step 4, you divide up your number line using those 3 critical values. And we're going to check a number in each region. So I check -3, -1, +1, +4. It doesn't matter what number you pick in your region, but you want to pick nice whole numbers, and if you can pick 0, do so. But in this case, you can't pick 0. It's actually one of your critical numbers. So you plug in -3 into the function. Now where do you want to plug that into? Well, you could plug it into here, but the easiest way is to plug it into the most factored form you've got, because this and this are the same thing. So if you plug -3 in here, you get -3 negative. You get -3 minus 3 is negative. -3 plus 2 is negative. Negative times negative times negative is negative, less than 0. So now let's try -1. -1, that's negative. -1 subtract 3, that's negative. -1 plus 2, that's positive. Negative, negative, positive multiplied together gives you positive, greater than 0. Then plug in a 1. Positive, negative, positive. Well, with 1 negative, you get negative. Then let's try 4. Positive, positive, positive. All 3 positives multiplied together gives you positive. So now we know negative, positive, negative, positive. So decreasing, increasing, decreasing, increasing. And we can say we have a relative min here at -2. We have a relative max at 0. And we have a relative min at 3. Okay? And so when we graph it, that verifies exactly what we found. Now, if the first derivative is 0, if the first derivative of f is 0 at some value of x, but it does not change from positive to negative or negative to positive as you check your signs here, like we would down here. If the sign doesn't change as you go from one critical value region to the next, that means that is not a max or min. It's called a horizontal point of inflection, which means that it's either increasing and then it continues to increase, or it's decreasing and continues to decrease. Sort of like x cubed. X cubed goes up, levels off, and then it goes up again. And so that's an example of something with the horizontal point of inflection where it levels off like that. Alright, so this one, let's find the relative max mins and horizontal points of inflection, or HPI. So you take the derivative, you get this guy, you factor it. Notice there's 4 terms, so try and factor something out of each one, and hopefully you can factor something out of the 2 larger terms. And then that part factors down even farther. You factor down and you get critical values of 2 and negative 2. You plug those into the original function to get the y coordinate. Now you know your critical points. And now you divide up the number line using 2 and negative 2. So we're going to try something like negative 3. We're going to try 0. We're going to try positive 3. And we're going to plug them into here. So if you plug negative 3 in here, you get negative 3 subtract 2 is negative. Negative 3 plus 2 is negative. Negative 3 minus 2 is negative. Well, 3 negatives multiplied together gives you negative. Now let's try 0. 0 subtract 2 is negative. 0 plus 2 is positive. 0 subtract 2 is negative. Negative times positive times negative, that's going to give you a positive. And now 3. Positive, positive, positive. So 3 positives multiplied together is positive. So you have minus, plus, plus. So when you have a change in sign, you know you have a relative max or min, assuming it's defined there, which it is. But when you go plus plus or minus minus, that means you got a horizontal point of inflection. You do not have a max or a min there. So you have a relative min at negative 2, negative 3 32 thirds, and you have an HPI at 2 32 thirds. You do not have a relative maximum here. So if you look at this, it's forever going up, so there is no maximum. It's just going up to infinity. And it does have a minimum point here, like we predicted. And notice right here, it levels off, and then it continues going up again. So you got increasing, increasing. That means that that is a horizontal point of inflection. Now you can use your calculator to locate places where the first derivative equals 0. So what you do is you take the derivative, and then you type in that first derivative into your calculator under y1, and you look where it crosses the x-axis. Now how do you find those points? You hit if you have a graph, you can hit second trace 2. Second trace 2 will give you what are called zeros. And what you have to do when you're finding a 0 is you have to move to the left of the point you want. So here's the point, one of the 3 points I'm looking for. Let's just find one of them. This one, I move to the left, which happens to be a little bit above, but it also is to the left. You hit enter. Now you move to the right of that point, hit enter, and then move back to the point itself and hit enter. And there you go, there's your answer. You can do it again. Second trace 2, and you move over to the next point. And you want to stop to the left of it, hit enter, then move to the right of it, hit enter, and then move back to the point itself, enter. And there's the second point. And the third one, second trace 2. Remember, when you're picking your left and right bounds, you want to make sure that they're far enough apart, because if you make them too close together, your guess that you do for the third number is not going to be in between, and it has to be in between the two. So there's your third place where it crosses the x-axis. And these are places, these are critical values. So you can find your critical values using that. You could also find it using a table if you want. There's many ways to do it. I think the second trace 2 is probably the simplest way. Example 3. So we bring the exponent up front and subtract 1 from the exponent, take derivative of what's inside there, because we're using the chain rule here, and we get a 1. And 1 times 2/3 is just 2/3, 2 over 3. And this crosses the fraction bar and is a positive 1/3, and you can write it as the cube root. So there's your first derivative. Now if you set that equal to 0, you don't get any solutions. But we know that it's undefined here if we're dividing by 0. Now what number is going to make this denominator 0? Negative 2. Negative 2 plus 2 is 0. 0 times 3 is 0. You're dividing by 0. That makes that undefined. So that is one of your critical values. Critical values are places where the first derivative is undefined or 0. Alright, so let's plug in minus 2 into the original function and we get 0, so now we know our critical point is negative 2, 0. We divide up our number line using that negative 2 value, and we check to the left and check to the right. So you check maybe negative 3, and then you check 0 with the derivative. Okay, when you plug it into the derivative, you get negative. If you plug negative 3 in, you get negative. And if you plug in 0, you get positive. So it's negative here and positive there, so it's decreasing and then increasing. Alright, so, but we do know, they put this little asterisk here, at least that's the way the book does it. That indicates that at that point, the first derivative is undefined. Alright, so we know that we're decreasing and we're increasing. And we know that that means we got a relative min at that point at negative 2. And if you look at this, it does have a relative minimum at negative 2, negative 2, 0. Number 4, they ask you over what interval are the sales decreasing or increasing. Well, you have to do the whole 5 steps here. So you have to take the function and take the derivative. You got to use the quotient rule, and then set the numerator equal to 0, the denominator equals 0. And see what you get. When you set the denominator equal to 0, it doesn't give you any real solutions. But if you set the numerator equal to 0, you get 10 and minus 10. But keep in mind, your problem says only from 0 to 20, so minus 10 is out. So 10 is your only critical number here. You plug 10 into the original function and you get 5, so 10, 5 is your critical point. And you divide up the number line. We only care from 0 to 20 because that's what the range, the domain is for our function. So for 0 to 20, the only number that divides up that region is 10. So we check S prime of 5 and S prime of 15. We could have done 9 and 11, doesn't matter. Any number between 0 and 10, any number between 10 and 20. So here we get positives, here we get negatives, so we know it's increasing, decreasing, so we know we have a relative maximum at 10, 5. And looky there, that's exactly what we got. So now they ask you, over what interval are the sales increasing? Well, from 0 to 5, or excuse me, 0 to 10. And in what interval are they decreasing? Well, between 10 and 20. And then B says, what are the maximum weekly sales? Well, that's at 10, when you plug in 10, and you get 5, and your answer is in thousands, so 5 represents 5,000. So your sales will be $5,000, and it's going to be in week 10. And now they say sketch the graph there, and you can see that we've sketched it right there. Now, with a graphing calculator, choosing an appropriate viewing window is key to understanding what the graph looks like. So to find an appropriate window, you set your X min of the window to the left of the smallest critical value. So in this case our critical value is 10, so you want to pick a number smaller than 10. You might want to try negative 5 or negative 10. And you pick the X max to be larger than the largest critical value. Well, 10 is the largest critical value, so you might want to go with 20 or 25. Okay? And once you've picked the right X values and you graph it, then all you have to do is hit zoom 0, and it will show you a nice good picture. Zoom 0 is the way of asking your calculator to adjust the graph so that the Y values are right. If you get the X values right on your own and just hit zoom 0, it will adjust it so that you'll be able to see your graph nice and easy. Alright, number 5. We have this function here. We take the derivative, we set it equal to 0, we factor. And now they ask us to find the critical values. So you take this guy and you pick a window less than negative 120 and greater than 100. Hit graph and then zoom 0. Now to find the relative max at negative 120, you just hit second trace 4. Okay, let me show you how that's done. If you want to find a relative max, like for this one, you hit second trace 4. Second trace 4, and you move to the left of your highest point, right there, enter, then move to the right of the highest point, enter, and then move back to the point itself and hit enter. And that will give you that maximum there. Now the fact that you get 4.9999998, that's really just 5. And you get 237.5. Alright, so let's find this minimum point. Second trace, and minimum is 3. Maximum is 4. We want 3 for this minimum here. And we're going to move to the left of that lowest point. Hit enter. Move to the right of that lowest point. Hit enter. And then move back to the point itself and hit enter until you get negative 4 2/3 and negative 214.1481. Okay? And so you can find your maxes and mins that way. Alright? So on this one, I actually wrote down what the window looks like. This is your X min, X max, and X scale. This is your Y min, Y max, and Y scale. Alright, example 6 says find a cubic model that gives the number of Americans working full-time as a function of their age. Alright, so here's what you have to do. You have to type in these X and Y values. The X values are the age, the Y values are the these 6.3 up to 3.54 numbers. Okay, so to type the data into your calculator, you're going to ask your calculator to come up with an equation. So to type the data into your calculator, you hit stat and then 1, and then you want to clear out numbers that were in there from a previous question. So you want to move over and arrow up until you highlight L1 and hit clear. Then arrow down, move over, back up and hit L2 and hit clear. Do not hit delete. If you hit delete, it actually gets rid of your list, and you don't want that. You want to hit clear. All right? So now you type in each number one right after another, hitting enter, and then move over and type in all your L2 numbers one right after another. And when you're done, then you hit Y equals. Okay? Hit Y equals, and you want to clear out all the equations that were in there. You want to arrow up to plot 1, hit enter, okay, and then you hit zoom 9. And when you hit zoom 9, your calculator will show all of your data points all on the same screen. So when you look at that, you have to decide what kind of equation you want. Well, they tell you it's a cubic model, so we're going to do a cubic regression. If this was simply U-shaped, we'd do quadratic. If it was lined up in a nice line, we'd use linear. Right? So this one's cubic because it curves up this way, but then it starts to curve back up. So you can see it's kind of like a cubic problem here. All right, so now you hit stat, arrow to the right once, and now you choose whichever regression you want. Linear regression, quadratic, cubic, quartic. We want cubic, so we're going to pick 6. Okay, so now you should have an L1 here and an L2 there, and these other 3 lines should be blank, so just hit enter 5 times. And there you go. There's your cubic equation, and that's your A, B, C, and D for each one. Now they ask you to round it to 3 significant digits. So if you take negative 3.6 whatever, E negative 4, that means you got to move the decimal over 4 places. So if the decimal is right here in between the 3 and the 6, you move it 1, 2, 3, 4 places because of that E negative 4. So that's actually the number you got, and for each one of these, those are the numbers you got here. Now how do you round this to 3 significant digits? Well, you count until you get to numbers that are not 0, and you round to the third one. So 361 with a 6 after it means it's 362. 400 with a 9 after it means it's 401. 138 9 with a 9 that 8 moves that 9 up by 1 to a 10, and that bumps that 89 up to a 90. All right, and 6791 leaves it at 679. All right, so now that you've got these rounded numbers, those are your A, B, C, and D, the numbers that go in front of each of the X values. All right, so now part B says find the relative max and mins of the reported function. Alright, so you just go back to example 5b where I showed you how to find the relative max and mins. If you typed this into your calculator under Y1, it'll look like this, and you find your relative min using second trace 3, and then you find your relative max using second trace 4, and you'll get these two values. Thus, the relative min of 6.3 means 6.3 million full-time workers at age 27.8 years of age, and a relative max at 7.4 million full-time workers at an age of 46.1 years old. All right, so now let's look at the questions that are similar to the WebAssign that you'll be looking at. Question 1, it says look at the graph and identify the relative max, relative min, and horizontal points of inflection. Well, relative max is right there at 1.5. Relative min is right there at 4.1. And point of inflection is where it's continually increasing or continually decreasing. This one's a relative or a horizontal point of inflection here at -1.2. Question 3 says use the graph of f of x in problem 1 to identify at which of the indicated points the derivative changes from positive to negative. At which point does it change from positive to negative? Well, that means it's increasing and then decreasing. Well, increasing to decreasing right there, so that'd be at the point 1.5. Where does the first derivative change from positive to negative? That's where, or B, changes from negative to positive. That's where it's decreasing and then increasing, so that'd be at the point 4.1. And then where does the first derivative not change sign? Well, it goes positive increasing to positive increasing, so the point -1, 2, which are exactly the same as in question 1. So when you have a relative max, you know that the first derivative goes from positive to negative. When you have a relative min, you know the first derivative changes from negative to positive. And when you have no sign change at all, you know you have a horizontal point of inflection. Number 5, it says, use the sign diagram to determine the critical values of f. Well, they're -3 and 7. B, find the intervals on which it's increasing. That's where it's positive, between 3 and 7. The intervals where it's decreasing, well, that's less than 3 and greater than 7. And then D, the x values at which you have a relative max. You have a max when you go increasing to decreasing, so your relative max is at x equals 7. And relative min, where you're decreasing and increasing, so your relative min's at 3. Okay, question 7, it says find the critical values, make a sign graph, and determine the relative max and mins. Alright, so you take the first derivative, factor it, set it equal to 0, and you find your critical values. You plug those into the original function, and you find your critical points. And now you check the number line, dividing it up with 0 and 4. Okay, and you're going to plug in numbers in each region, so -1, +1, +5, and you want to plug it into the first derivative most factored form. And here you get plus minus plus, plus minus plus, so you know it's increasing, decreasing, increasing. So you got a relative max at the point 0.06, you got a relative min at 4, -58. Question 15. Find the derivative, find the critical numbers, critical points, and we're doing all 5 steps here. So find the first derivative. You get this guy, set it equal to 0 and solve, that's your critical value. Plug that into the original function and you get your critical point. Divide up the number line and check a number on each side and you get minus plus, so you know you have a relative min, there is no relative max. And you know it's increasing greater than 1, you know it's decreasing less than 1. And when you graph it, there you go. That's exactly matches with what we found, what our data told us. 17, same idea, all 5 steps. So we take the first derivative, we get this, we factor it, set it equal to 0, we get our critical values. Plug those into the original function to get our critical points. Now we divide up our number line using those 2 critical values and we check a number in each region and we look for the sign in each region. And so now we know plus minus plus, so we're relative max, relative min. There is no horizontal point of inflection. It's increasing less than -2, and it's increasing greater than 1. It's increasing between -2 and +1. And here's the graph that justifies all of that. Number 19, you take the first derivative, and you want to rewrite it as nicely as you can. Set that equal to 0. There's no solution for that, but there is a place where you're dividing by 0, so that's an undefined value. So you have a critical value at 0. Plug 0 into the original function, and you get 0, so that is your critical point. Divide up your number line into two regions here, divided by the one critical value you have of 0. And when you check the first derivative in each region, you get minus plus, so you know you have a relative min there. You know it's decreasing less than 0. You know it's increasing greater than 0. So you have a relative min at 0, 0, and that's what your graph looks like. 25, you take the first derivative, factor it, set it equal to 0, and you find you have one critical value of 1. Plug that into the original function, and you get 4/3, so that's your critical point. Divide up the number line with 1, and with both of these you get positive, so you get plus plus, so it's increasing and then it's increasing again. So that means no sign change means it's a horizontal point of inflection, and it does not have a max or a min. When you graph it, look, it doesn't have a max or min, but it does have a point of inflection, horizontal point of inflection, because it's increasing, then it levels off, and then it's increasing again. 27, we take the derivative, we set it equal to 0, and we get critical values of -6 and 4, and you plug those into the original function, and you get 128 and -115/3. Those are your critical points. And now you divide up the number line and check a number in each region, and you get your plus minus plus, so now you have relative max, relative min. And when you graph it, it all matches up exactly with what we found. 29, take the first derivative, set it equal to 0, and you get 3 critical values. Plug those 3 into the original function, you get your 3 critical points. Divide up your number line, and you get plus, minus, minus, plus. So plus minus is relative max, minus plus is relative min, minus minus or plus plus is a HPI, so we got a HPI there. Alright, so relative max at -1, 3, relative min at 1, -1, HPI at 0, 1. And looky there, relative max, relative min, and HPI forever decreasing, so that's a relative HPI. That's how that works. Alright, so this one says, this is a graph of the first derivative, not the original function. So they say use the graph of the first derivative to determine the critical values of f. Remember, the critical values of the original function f are where the first derivative equals 0. So where does the first derivative actually cross the x-axis? At 0 and at 3. So those are your critical values. Now they ask you to find out where it's increasing. Well, it's increasing where the first derivative is positive, greater than 3. It's decreasing where the first derivative is negative, below the x-axis. So it's decreasing for less than 0 and between 0 and 3. Now you could technically say x less than 3, but you also have to say not at 0. Because at 0, it's technically not increasing or decreasing. Right, so relative max, it doesn't have one. Relative min, yep, it has one at 3. And HPI, it has one at 0 because you have a negative and then you have negative again. So the fact that it goes negative, negative, positive means you got a HPI at the first one and you got a relative min at the second one. And they ask you to come up with a possible graph, and this is what it could look like. One of many choices for the function. Alright, so this one you take the derivative, set it equal to 0, factor it, you get your answers, but keep in mind we're restricted to 0 to 8 here. So the fact that we get -14/3, we got to throw that out, so we only have 5. Now when we draw a number line, we only care from 0 to 8, and we divide it up with 5, so we check numbers between 0 and 5. I tried 1, and greater than 5 and less than 8, we tried 6. And we got plus minus, so increasing, decreasing, it's got a relative max at 5. and it turns out to be 237.5. So it's increasing from 0 to 5, it's decreasing from 5 to 8. 53, when you take the derivative, when you take the derivative of 5,000x, you just get 5,000. When you take the derivative of this guy, I wrote it this way to make it easier. You get negative 125,000x to the negative 2, which you can write over x to the positive 2. Now when you're trying to find critical values, you might want to write this as one big fraction. So take this guy and multiply this one by x squared over x squared, so you can write it as one big fraction. Now, when you go to solve this, you can solve the numerator equal to 0 and denominator equals 0. Okay? So when the numerator equals 0, you get this, you factor out the 5,000, and what's left factors as well. So when you set all that equal to 0, you get 5 and minus 5. You'll also get 0, because you can't divide by 0, but our domain is greater than 0, so 0 is not a critical value, and neither is negative 5. So our only critical value here is 5. Because our interval is greater than 0, we only have one number that divides up our region. It's 5. So we check a number in this region and a number in that one, and we get minus plus, so we know we have a relative min at 5. So it says find the critical values. We did, x equals 5. It says over what interval is the average cost decreasing? Well, it's decreasing from 0 to 5. And where is it increasing? It's increasing greater than 5. All right, 54. They give you the average cost of mining operations depend on the number of machines used, and the average costs in dollars are given by this, where x is positive. It says find the critical values of that function. So you have to, I rewrote the function this way so it would be easier to take the derivative. And then I simplified it and wrote it all as one big fraction. I set the numerator equal to 0 and factored it, and I got 21 and minus 21. My denominator is where it's divided by 0. I got 0. But remember, we only care about greater than 0. So equal to 0 is out, minus 21 is out, so the only one that matters here is 21. So if we're looking at greater than 0 to infinity, and we divide the number line using 21, we can check numbers in this region like 1, and we can check 22, and we get minus plus, so that means it's a relative min, and then a relative max. So, question part A says find the critical values, 21. B says over what interval are they decreasing? Well, they're decreasing from 0 to 21. Over what interval are they increasing? Well, they're increasing greater than 21. How many machines will give minimum average cost? Well, you get a relative min at 21, so 21 is your minimum number of machines. And what is that minimum average cost? You plug 21 into the original function and you get 121,800. That's your minimum average cost. You plug that into the original function, not the derivative. Alright, so marginal revenue is given here. It says at each of the different values what is happening to the revenue. Keep in mind this is marginal revenue, so this is the derivative of the revenue. So at x equals 150, your marginal revenue is positive, which means that the original function is increasing at that point. At x equals 250, it equals 0. So that means it's not increasing, it's not decreasing, it's changing from one to the other. And then at 350, it's negative, which means the original function is decreasing. B says over what interval is the revenue increasing? Well, it's increasing where the first derivative is positive. That's 0 to 250. How many units must be sold to maximize the revenue? Well, if you hit at 250, you're changing from increasing revenue to decreasing revenue, so that is a maximum at 250. 57, they say find the critical values, and they say for how many weeks will weekly revenue increase. So you take the first derivative, set it equal to 0, and so you set the numerator equal to 0, and you get these this factored form, and you get these two numbers here. Set the denominator equal to 0, and it doesn't give you any answers. We want t greater than 0, So we throw out the negative 6, so our only critical value is 6. So we want greater than 0, and we divide up the number line using 6, so we try numbers in this region of 1, numbers in this region of 7, and we get plus minus. So increasing, decreasing, looks like we have a relative maximum happening at week number 6. So it says find the critical values. Well, it's t equals 6. And then it says for how many weeks will weekly revenue increase? Well, it's increasing this entire first 6 weeks, and then it's decreasing. So it'll increase for 6 weeks. And the last question talks about medication in the bloodstreams after a certain number of hours. So you take the first derivative and simplify it down, and you factor the top, you factor the bottom. The bottom doesn't give you any answers, but the top, when you factor it, it gives you t equals 1 and t equals negative 1. Now we're talking about time here, so you can't have negative 1 hours. That's out. So t equals 1 is your only critical value. Divide up the number line greater than 0, and so you got 1 here, and when you check 1/2 or 0.5, you get a positive with the first derivative. When you plug 2 into the first derivative, you get a negative. So you got a relative max here happening at time 1 hour. So it says determine the number of hours before C attains a maximum. Well, it attains a maximum at hour number 1. So after 1 hour, it'll achieve a maximum concentration. It says find that maximum concentration. So you have to plug in that t equals 1 into the original function, and you end up getting 0.1, whatever that is. It could be grams, could be ounces. You don't know what the measurement is. They don't give it in the question.